now. So we'll begin this session today with a talk about convex sets and functions. So I mentioned earlier that the optimization problems, in optimization problems, certain classes of optimization problems are far easier to solve than others. In particular, the concept of convexity, both in terms of functions, meaning the cost function, and in terms of the sets that make the feasible set. In both situations, convexity is a very necessary, well, not necessary, but very helpful property. So first we will go and define the concept of convexity when we have a vector space, and we define a convex set. And the intuition about behind the convex set is fairly simple. Just see if I do some annotation here. So the idea of a convex set is that if we have a set K, and I'm just, this is probably not going to be convex really as a drawing, but never mind me. Let's say this is my set K here. And the elements here are vectors of some sort. Of course, in this picture, because I'm drawing it like this, it's a two-dimensional space, but you can have the dimensionality of this set can be any vector space, basically. And if you don't know how vector spaces work, I mean, we'll look at that appendix later, but think about this in terms of we have points, and then we can multiply those points with constant numbers. So the idea here is that if we pick 2 points here, let's call that X, let's say that's X, and we take point Y, that's my Y. And then I make what is called a convex combination of it. So I take here some combination of X and Y. So this should be a straight line. Again, I'm sorry that I'm not being able to draw a straight line here. So basically what this definition says is that all the points that join X and Y along a straight line, they are also inside this set. So this is a convex set because, you know, basically if this happens, well, obviously I made a small nudge there on the edge. So this is not really convex, but let's say that this is convex. So I'll give an example of something that is not convex. So this might be a set that looks like this. And in here, I have X, and in here, I have Y. And if I draw a straight line from X to Y, like so, let's assume that it is straight, then these points here, for instance, that point over there, it falls outside the set. So this is not convex. So convexity means like that the edge of the set doesn't have these indentations or it doesn't curve inwards anywhere. A simple example of a convex set might be a circle or a cube or a rectangle. Those are all convex because if you take 2 points from that set and you draw a line between those 2 points, then all the adjoining points are still inside that set. So that's the basic idea of convexity. And I'll show you shortly why convexity is such an important notion. So this generalizes to any vector space. So if we have 2 vectors that have real coefficients, X and Y, in a vector space that has real numbers as coefficients, or if it's easiest to think of this maybe as Rn or R2 even, then if you take X and Y and then any number between 0 and 1, and then you multiply X with that lambda, and then multiply Y with 1 minus lambda. So you see that as lambda ranges from 0 to 1, this combination here is some point between X and Y, just like along this straight line. And if all those points are in my set, regardless of which X and Y I pick, then the set is convex. So that's the meaning of convexity here. So we'll be discussing convexity a little bit more today. Right. So let me just Oh, I have to take this annotation. So some examples. Clearly, if you have an empty set is convex because, you know, looking again, you should be familiar with these pretty basic mathematical borderline cases. Like the empty set usually has the property that you're talking about. So take any two elements from the empty set. Well, it doesn't have any elements, so, you know, this is what is called vacuously true. If we take X and Y, then something holds, but because we cannot take X and Y, then it's always true. Empty set is convex. The whole space, you know, when we're dealing with vector space, then, you know, a vector space is a space which is closed under linear combinations of all vectors. So the space itself must be convex because you can just have any combination, it's still inside that space. If X and Y are both in that set, we only need to check it for values that are between 0 and 1. We don't need to check 0 and 1 separately because we already assumed that X and Y themselves are in that set. So let's talk about this convex sets a little bit. What kind of properties do convexities have? So the intuition there in the intuition behind convexity is that the set is, if you look at the edge, I mean, this is geometric intuition, and it's not entirely accurate to generalize this, but if you want to think in what convexity means, is that if you're looking at the edge of that set, so there's, let's say that underneath are the elements that are inside the set, and over here are the sets that are elements that are I have this, so that are outside the set. So if we look at that set, then the border of the set, then the border of the set never has this kind of inward bending region in it. It always kind of curves on the outside. So this concave, which means this, and then convex, which means, you know, this outward bulging. So the edge of the set bulges. If it bulges outwards, never inwards. And if we have a vector space where we have a convex set K, then we can scale this set. So we take any elements X from that set K and multiply with alpha, and then we gather those in one set. Then this will be convex. It's fairly easy to prove. I'll show you these statements, and we'll show some of these proofs here. And then I'm asking you guys to go through it on your own, and later to do it in the exercise as well. So the sum of two sets, meaning you take one convex set and you take another convex set, and then they take all combinations that you can get by adding elements from one with elements of the other. And that results in a convex set as well. Also, if we have an arbitrary collection of convex sets, then their intersection is convex. For the union, this is not necessarily so, and I can draw you a counterexample why the union is not always convex. I mean, let's say that this is a circle which is convex, and I have here another circle which is also convex, and the union will contain all of these points in both of these circles. If I take the point here and take a point there, and I draw a straight line between those from here to here, then I notice that at that one point over there, it goes, well, in those points over there, it goes outside the set in there. So, you know, the union of two convex sets is not convex. The intersection is, that's the region at the intersection there. That is convex, but the union is not. But if we have what is called an increasing sequence of convex sets, meaning that the first set, the first set is like this. Let's say that for argument's sake that this is a convex, and it's an increasing set, so that the next set is larger than this and still convex, and it contains the original one. So we're just increasing these. If it's an increasing sequence of convex sets, then the union is convex. Well, obviously, if we take it up to infinity, it needs to be done separately. But if we consider any subsequence, then of course, this union is always just the last one over there. The point here is that by increasing a set gradually, relaxing constraints or pushing the boundary onwards, ensuring that every step of the way it's convex, you cannot break convexity, even if you do it to infinity. Okay, these are very important concepts and important properties of convexity. And now the tie-in or the connection as to how this relates to optimization problem, we will explore this during these lectures now. So why do I do it like this, and why do I give you an example of an optimization problem? Well, I think the idea of convexity in terms of as a mathematical concept is a very generic and very important concept. So I think it's reasonable for me to teach it to you and have you understand it. Oh, it seems that I didn't have a video of myself, by the way. Yeah, here I was gesturing with my hands. Sorry about that. It's not showing you well. All right, let's continue. So how do we prove these things? Here are some of the proofs are included in this material. But let's first go through this material here. So very often we define what is called a line segment between X and Y. So this notation X, Y in these brackets, this is something that is probably familiar to you from your previous courses. You know, you write this for real numbers. Oh, that's too bad. Oh, you cannot see the text editor. All right, but you can see the slide.
Yes, slide is visible. However, any other.
See the drawings as well that I.
Yeah, we saw the drawings, but.
Okay, good.
Yeah,
Then the text editor is not important. I try to avoid that. All right. Thank you. So if you look at here, the line segment, look at this notation here. We have this X, Y. So this is familiar to you probably from previous courses. You may be used to this notation. So there's a closed interval between two numbers, let's say 5 and 6. So this is the closed interval of all the real numbers that are larger than or equal to 5 and smaller than or equal to 6. So that's like includes 5, 6, and then any number between. We generalize this to all vectors in the following way. So you have all the vectors Z that are expressible by taking lambda times X plus 1 minus lambda times Y for some lambda from 0 to 1. It means that when you pick lambda equal to 0, you get X. When you pick lambda equal to 1, you get Y. And for numbers between 0 and Y, you get some vector that is on the straight line that joins X and Y. All right? So basically we can say convexity is the property that the line segment that joins 2 points of arbitrary elements in the set is always completely inside that set. Convexity can be characterized in the way in real numbers is that in fact exactly all the intervals are convex sets and no other convex sets in the real numbers exist. So if we have a set of real numbers you know, where you know, it's not vectors, it's just one number. The set of real numbers is our space now. Then a convex set is always one of the following. It's either an open interval between some two numbers, half closed, so that, you know, the other end is included, but the other is not. A closed interval, so that both ends are included. An unlimited interval, so all numbers smaller than some number A, or all numbers that are larger than some number A, or the whole real set of real numbers. No other convex numbers exist. Convex sets of real numbers exist. And we can prove this. And let's just go through this proof, and after we've gone through this proof, we'll do a little bit of group work right then. All right. So let's prove this. So how do we prove a concept like this? And why do we, more importantly, why do we prove this? Well, one of the things is that I want you to be able to gather some intuition about what do these convex sets look like. And if you're dealing with a optimization problem later, then you will be able to understand that, okay, this kind of problems will be convex. I can use whatever methods are available for me in convex optimization. And if it's not convex, then I have to use some other methods. And also, I think in terms of just, you know, being more knowledgeable in mathematics in general, because convexity is a very common property and very, very important property. Okay, so let's start. Firstly, if we have just a degenerate interval here, meaning that it just consists of one point, and that's convex, but it's convex because, you know, there are no other points except that one point, and all the points are on that one straight line, which just degenerates into one point. So there's nothing to prove. So we assume that this interval has at least 2 points. So we already know that every interval is convex. It's fairly easy to see because the line segment can be just expressed like this. So for obvious reasons, every interval in itself is convex because all the numbers between A and B are in that interval. If we have that, you know, it's by definition, all the numbers between the A and B are between A and B, right? So we need to prove that every convex set is an interval, though this is harder. So if we have a convex set, it must be an interval of some sort. So there are these different cases, and I'm going to go like prove the different cases case by case. Are you familiar with this concept of infimum and supremum? I'm not sure if you are familiar with the concepts of infimum and supremum. So infimum means the greatest lower bound. So it means that let's just take the idea that numbers are from up and down, right? And smaller numbers are down and larger numbers are up. And we have some set of numbers here, you know, larger and smaller. Then you can think of the infimum as us setting a limit from below as high as possible so that you know, no numbers from that set fall below this, right? It's the largest lower bound. So we make it as big as possible without any number in that set going below this level. So then that's the infimum. And the supremum, on the other hand, is the least upper bound, meaning that we make it small. It's a limiting number, and we set it as small as possible so that no number in that set is above it. So the least upper bound and the greatest lower bound. Infimum is the greatest lower bound, and supremum is the least upper bound, right? So upper bound is something that we set a line, and all the numbers in my set, you know, I is the set here. So the sub I, if we are looking for that, then any number that is larger than anything in that set is an upper bound. But if we make it lower and lower and lower and lower and lower, and eventually we get to a number that if we make it any lower, then some of these numbers in I will be bigger than this limit. So that's what supremum means. So let's take the least upper bound as B and the greatest lower bound as A. And we check these cases. If both A and B are finite, it means that this I doesn't contain infinitely big numbers. There's a limit, both upper and lower limit. Good. If we have a number that is smaller than A or larger than B, then obviously it's not in that set because we have a lower bound and an upper bound, right? Anything lower than the lower bound will be outside the set, and anything larger than the upper bound will be also outside the set. So we know that this interval is contained in the closed interval A and B. Now, if we take a number from the open interval between A and B, so we have the upper bound and lower bound, we take some number between those upper and lower bound, but not equal to the lower bound, by the way. Then by the definition of this supremum and infimum, because A is the greatest lower bound, and we take a number bigger than that, then there must be something between A and X that is inside the set. Also, because B is the least upper bound and X is below B, then there must be something between B and X that is also in that set I. So it's in this we're taking those two numbers, the one that is closer to this lower bound as X1 and the one that is closer to this upper bound as X2, right? So we have that this X1 is between A and X, and this X2 is between B and X. And now because I is convex, then all the numbers between X1 and X2 are contained in my I. It's convex, right? And we conclude that the open interval from A to B is contained in I. So the interval it contains the open interval, sorry, not the interval, the set I, which was stipulated as being convex. It contains the open interval between A and B, and it is contained in the closed interval. So, but there are only 4 sets that can be discussed here. The open interval between A and B, then the two semi-closed intervals. Either A is included and B is not, or B is included and A is not, or both A and B are included. So there are only 4 sets to consider, and we've now stipulated or proven that this I is one of those. So this I is an interval, either it's open, closed, or semi-closed, but there are no other possibilities here. So there we have it. The infinite cases, I'm not going to go through the infinite cases. You can, I'm just sorry about that. I'll do that. Clear that line there. Sorry. The infinite cases, I'm going to just skip them and so forth. All right. Now we've explained some of the things that happen with the convex sets. This theorem was not proven really here. We didn't prove it. We will proceed to prove this during the exercises. But what I'm going to do now, I'm going to pause the recording. Now resuming the recording, and we're moving on. So, like I said in the earlier, the convex set, you can think of the intuition as being, you know, the border is always bent outwards in some sense, but it's the mathematics is that 2 points, the adjoining line between 2 points is always completely inside the set. That was the convex set. There is a great connection to functions. Well, we don't usually think of functions, you know, now we're talking about just functions like we usually do, real valued functions and so forth, but now vector functions, that how do we characterize convexity of functions and what is the connection between functions and convex sets. We'll discuss this next. So the idea of optimization algorithms is more often than not, it's based in a model-based approach, so that we form a sequence of points, x1, x2, and so forth, and theoretically speaking, up to infinity, you know, an infinite sequence of points, ones that approach the optimum, hopefully, if the method is properly selected, that this limit of this sequence is the optimum point. And it is done so that we take a point in this sequence. So let's say take the first point. We approximate a function in some neighborhood of this point. So, you know, we don't look at all the possible values. We just look how the function behaves close to this point. And then we move on. We do this by selecting not the original function, but some approximating function, which is to be convex. And convexity of functions, or convexity of sets, was defined in, like I said, you could think of it as there being an edge that never bends inward. Then we can think of convexity of functions as something that guarantees that the function forms like a cup of some sort, so that if we keep on moving along the lines, no matter where we move, if we move into a direction where the function grows smaller, we eventually hit a bottom, and the bottom is such that, you know, there are no, it doesn't then bulge upwards anywhere. So there's a connection there. The ideas are similar, and even the definitions are similar, and the mathematical connections will be fascinating. We'll look at them next. And very often we want to use convex functions because of this property in these iterative methods. So let's say that we have a convex set, and now we want the set to be convex. Usually we deal with the whole set of our discourse, meaning that if we're optimizing a n variable model, then we're talking about Rn, you know, n dimensional real vectors, for instance. But it can be some subset of it, like it could be an n-dimensional sphere, for instance, you know, the ball, everything inside the sphere, or something like this, as long as it's convex. And we have a function that is defined in that convex set. Again, remind you that what that set K is not that much important. We want it to be convex for this definition to be meaningful, but usually we can think of it as being the whole space. If we have the property that when we take number x, we take the vectors x and y for which this function is defined, and then we move along the adjoining line between x and y, then the function's value in those points between x and y is smaller than or equal to the combination of the values of the functions at the end. So this basically can be thought of in this way. I'll draw you something. So let's draw here. This is my coordinate system, and I have here x, and I have here y, and I have here, I have here the line that joins x and y, right? That's the line that joins x and y. And now I'm going to draw the function. Then what is guaranteed is that the function is here below this line. And this is guaranteed intuitively if the function curves upwards. This is an example of a convex function. Well, not exactly, of course, my hand is a little bit wiggly there, but let me give an example of a function that is not convex. It might be something that does something like this. This is not a convex function, because if you take, for instance, that point, and then you draw the adjoining line, then between here, the function is above that adjoining line. On the other hand, if the function is curved like this, then no matter where we draw the adjoining line like this, then the numbers, you know, the value of the function between these 2 points is always below that line. But of course, these are all just one-dimensional cases, but this applies to larger dimensionalities. During the exercise, I'll show you some two-dimensional cases for which we can actually draw pictures. For higher dimensional cases, we can't really draw pictures because, you know, well, 3D, we could probably do some kind of 3D plot, but it's already a bit messy. But with 2D, we can at least draw some examples. But if you can think of it, if you think of it in terms of two-dimensionality, let's say that this up-down is the value of the function and it's in a two-dimensional plane. We're moving and we're looking at the value of the function. Then the convex function forms, let's say we're evaluating it inside a circle, then the convex function has this, it forms this sort of a cup-like. It doesn't have to be it doesn't have to curve upwards like this, because, you know, it can go, for instance, it can go like this, ever sloping, you know, it goes downwards there up to infinity. But whenever you draw, the key issue is that whenever I draw a line like this that adjoins 2 points, then between those 2 points, it's below that, the function's value is below that line. At the extreme, at the extreme, of course, it may be equal to the numbers on that line because it is smaller than or equal to. And in fact, we say that it is strictly convex if it's strictly below that line here. And conversely, if this comparison is the other way around, we say that the function is concave. And perhaps the easiest intuition about this convexity of a function is that, you know, the graph of the function is like this cup, and if it's concave, it's this hill, right? And you can understand why, if we want to optimize a problem, then a convex function is very nice, because we can just go down the slope from anywhere, and you know, there's not going to be going back up and then back down again. So let's look at some of the examples here. For instance, if we have a linear function, what is the linear function? A linear function is a function such that I'll draw this, well, I don't have this yet, but the linear function is such that if we take g of ax plus by, then it is a times g of x plus b times.
We cannot see the black.
I know you can. I know you can't see it, but I'm just writing it here. Though I'll copy it and I'll paste it so that you will see it.
Okay.
I understand that. So I wonder if this is the text. So it's sorry. I'll make this a little bit wider. So a function is now this you can see. So a function g, like a and b are now scalars. These are, for instance, real numbers, and x and y are vectors. And we say that g is linear if it has this property that g of ax plus by is a times g of x plus b times g of y. And we say that it's linear, right? And if it has an additive quality to it, so that there's a linear part. In this case, we have this f of x, which is called an affine function. It has a linear part and then some offset, in this case, c. Then this affine function is always convex, and we can easily prove it here. Well, the proof is fairly simple. We take f of this linear combination, or this convex combination. By the way, we say this lambda times x plus 1 minus lambda times y. We call this a convex combination of x and y if lambda is between 0 and 1. Then a convex combination of x and y, then we can calculate the value. It's g of that convex combination plus c. And then we can rewrite this because of linearity, then oh, sorry. Oh, I accidentally did that. That was good. Sorry. So here we have this G and, sorry. If we have this G and we take, G is linear, so it becomes lambda G of X plus 1 minus lambda G of Y. And then you can write C as lambda plus 1 minus lambda times C, because lambda plus 1 minus lambda is obviously 1. And we can rewrite this as lambda times G of X plus C plus 1 minus lambda times G of Y plus C. And that's actually equal to lambda times F of X plus 1 minus lambda times F of Y. So affine functions are convex, not strictly convex, because for affine functions, this comparison is an actual equality, not an inequality, but they are convex nevertheless. So affine functions and linear linear problems are very important subclass of these problems because they are convex, well, among others, because they are convex. Here's an example. If we have an interval of real numbers, and if we have a function f of x is equal to x squared, this is strictly convex. And this is algebra. I urge you guys to look through it. I'm not going to go through this in detail. It's fairly simple. You just substitute this lambda x plus 1 minus lambda y, take the square of that, and then do a couple of approximations. You know, and you can prove, this is the way you can prove that in fact it's strictly convex, so that if you take the convex combination, the square is always smaller than the convex combination of squares. So the square of a convex combination is smaller than the convex combination of squares. And so the square, you know, x squared, x to the power of 2, that's a convex function. We'll shortly see ways of proving that functions are convex that are more generic than just trying directly the, well, not generic, but more easily done, more abstract than simply just substituting these for this equation. But it's a good handiwork to go through these simple examples. It gives you an idea of what is going on. Here are some theorems. Well, here's one theorem that gives the basic properties of convex functions. The proofs here are left as an exercise. We'll go discuss this during the exercise session, so that will be either Thursday or Friday, depending on which one you attend. So, if we have two vector spaces, x and y, we have a convex set inside that set x, and we have some interval of real numbers. Then the first property that we can prove is that if we have a set of convex functions, f1, f2, and so forth, up to n, if we have n convex functions, then their positive linear combination is convex. And by positive linear combination, we mean that each of these is multiplied, fi is multiplied by a positive number, and then these results are added together. So this is what is called a positive linear combination. So we have a coefficient for each f, which is between 0 and, well, it's more than 0. Then this function is in fact convex. This means that if you take a number of convex functions and each of them contribute in a positive way to the result of the function, you add them together, then you get a convex function. This is highly important in some applications where you have additive properties in the model. So we'll show some examples later. Another property is that if you have convex functions, n convex functions, then if you always at all points choose the maximum of those functions, the result will be convex. The resulting function is convex. So we have n different functions. They get different values at different places. The only thing we know about these n different functions is that all of them are separately convex. then at all points we take the maximum of those two, then the result is convex. Let me give you an example here. I'll draw you a, again, a one-dimensional example. So let me say that this is my first convex function. It's the graph of a convex function. I'll use different colors. Here's another one. It's something like, let's say it's something like this. Let me have a third one, which, let's say, for argument's sake, it's a affine function. It goes like this. So the maximum here, and I'm going to just pick a color, I'll use purple here. So the maximum would be something like it goes through here, it goes to there, it goes through there, and there. This purple, well, it doesn't show very well, but the maximum goes along this line. Always choose the biggest. And that function will be convex, always. So this is a very important property of convex functions, is that if you take the maximum of convex functions, the result is convex. Transformations, for which it's hard to make drawings now here, but transformations, if you have a decreasing function and another function which is concave, then if you combine these two functions, then the result is convex, and vice versa. If you take a decreasing function of a convex function, the result is concave. On the other hand, if you take an increasing convex function and another one which is convex function, and you apply the increasing function on that convex function, then the result is convex. So let me give a very simple example. I'll write it in text. So make it a little bit bigger here. That's an example. G of x is equal to x squared. F of x is equal to minus x. And now if we take, let's say g of x is minus x, because I'm taking that. And h of x is x squared. So if I take the combined function g of h of x, then that's minus x squared, right? So this is an affine function, which we know to be minus x. We know to be what's linear. So we know it is convex. We apply that to h of x, which is x squared, which we already proved to be convex. We get the negative of x squared. And this is a concave function. Its graph looks like this, right? I'll get, the inverted parabola. That's an example of C. An example of D, increasing and convex. Let's give a little bit more complicated example. Increasing and convex function. Let's say K is the set of x greater than 0, right? So we're taking all numbers that are greater than 0, and my h of x is the square root of x. Sorry, that is not, the square root is not convex, but the negative of the square root is convex. And my g of x is an increasing, I want it to be increasing and convex, so I take x squared. It's increasing because we are talking about positive numbers now, then it's increasing, right? Then the g of h of x is in fact, it's in fact x when we're dealing with positive numbers again. this is a convex function. Again, if we combine a convex function and an affine function, meaning that you can express it as a, an affine function is one that you can express with a linear part plus something. So that's in matrix / vector notation, it's ax plus b. So h of x is ax plus b. It's a linear function. You multiply first a vector with a matrix and then add some vector to it. Then if you impose a convex function on, if you take a convex function of this affine function, then the result is a convex function. So it means that you can, convex functions don't work just as well as before. I mean, before we saw this union of convex and in certain situations, and the intersection of convex sets in all situations result in convex sets. But if you take a convex function of a convex function, the result is not necessarily convex function, but if it's convex and increasing, the second one you take, then the result will be convex. So, you know, this doesn't behave all that well, but it does behave well if the other functions besides the convex function are affine functions. And if the last thing you do is take a convex function of that, then your set, you still have a nice convex function. Also, and this f, I cannot stress enough, this is the most important reason, I mean, one of the most important properties in this whole scheme of optimization. If you have a function that is convex, it maps, you know, some vectors to real numbers, it's a convex function. Then if you define a set E in such that pick all x's from this domain of this function such that f of x is smaller than c, then that is convex. This means that if we define a optimization problem where there's a minimize some function, forget about that now, subject to, and then oh, sorry, I have to pause. The battery is about to die. Just a second. All right. So what I was saying is that if you have first a bigger convex set, then you have a function that is defined in that convex set, and now you impose a limitation so that take all the numbers from this, all the vectors from this set such that f of x is smaller than or equal to c. Then it's not all of this, it becomes smaller. But what happens is, what you get is a convex set. And this is the important connection between convex functions and convex sets. This is the important connection, this f. And I cannot stress enough how important this is. And this proof we will go through during the exercises in a lot more detail. All right. Now, let's have another session of group work a little bit. So go through this, these points here and come up with very simple, I mean, you can use don't need to use vector functions except for f. You have groups 1, let's see, you have room 1, 2, 3, 4, 5, and 6. Okay, yeah. So you have 6 rooms. I think I'm going to recreate the rooms because now we have 5 rooms, right? And I'm going to give you a task. So come up with the examples of these points: A, B, C, D, and E in each of your group. So room 1 gets A, room 2, sorry, room 2 gets B, room 3 gets C, room 4 gets a D, and 5 gets E. And come up with examples, and you can just have real valued functions here. Come up with an example. In A, 2 functions are fine. In B, 2 functions are fine. In C, decreasing and convex, and a concave function, increasing and convex, and so forth. A very simple example, and I'll give you each group 15 minutes to do this. And again, because there are now the groups are now new, then spend a couple of minutes again introducing each other to the group, and then come up with a very simple example for A, B, C, D, and E according to your group number. I hope everyone is set, and I'll give you 15 minutes to do this. All right, we'll get back. recording on. So this is what I've had. So like I said, if we have a convex set, then the function that is differentiable and continuous is convex if and only if we approximate f at x by taking the derivative at y and then looking at the distance that we travel from y to x, then the approximating with that derivative gives a lower approximation of the actual function value, or that when you draw these tangents of the function, then the function tends to slope upwards from that. And a situation where it's not true is where it just bends downwards from those tangents. And here is a proof which we will not go through, but we see here that we need to reference theorem B21 and reference these B theorems. So the next week, what we will do is we'll take a small detour to the B section and talk about the analysis, talk about the real analysis part of this and the function theory part of how we can go through this proof. Not going to spend too much time on it, but we'll talk about that next time. All right, so study this proof on your own. We will look at it next week, but it's very important to understand why this works. And then later on, when we develop these methods where we calculate the derivatives or the gradients, if you will, and in order to find where that gradient is 0, then we know how to find a minimum of convex functions. All right. That's all I have for today. I'm going to now stop.